When you learn a second language, you have to learn how to conjugate verbs. When you learn your first language, whatever that first language was, no one ever has to teach you how to conjugate a verb. You just learn it by acquiring the language. Like nobody, when you were little, if your first language was English, you didn't have to like consciously think the difference between run, running, ran, runned. You know, we just, yeah, run is not a word. And so, but you don't have to, or will run, or I am going to run. You don't have to, nobody has to teach you that. It's something you consciously come up with. But when you're learning your second language, someone has to teach you how to conjugate that verb into the different tenses. Same, the word differentiable. We've got to differentiate. We have differentiability. We have is it differentiable? All the different forms of the word differentiate, all coming from the word derivative. I still am not really sure how the word DERI, derivative, that's the noun, turned into the verb differentiate. I don't really know how in the English language that happened, how we went from DERI to DIFF. Doesn't make sense to me, but there we have it. We have the noun is derivative. The verb is differentiate. The adjective is differentiability. Okay. The modifier is differentiable. So you have all the different forms of that word. Okay, so to differentiate, to differentiate is can you take the derivative of something? There are a couple ways we need to talk about differentiability. One is visual differentiability. We talked about visual continuity as well. So visual differentiability. When we talked about this with continuity, you could just look at something and say, yes, it's continuous, or no, it's not. It's broken. I see a gap. I see a removable. I see asymptote. Okay, you can just look at something and have it know if it's continuous or not. You can look at something and know if it's going to be differentiable or not. Then you just got to prove it. So visual differentiability, these are the things that you're looking for. No corners. So what classic group of function gets thrown out automatically? Absolute value. Okay, absolute values are thrown out. Right, no corners. No something called a cusp. All right, a cusp is, well, a corner is formed by two straight whats? Two straight lines, okay? A cusp is two curves connected to each other whose slopes are both infinite. And so I'll show you, it's like I think of it like a wave, kind of like this, like if you've got that side connected to that side, that would be a cusp because they're two curved things and both they're coming to a peak like that, so that's a cusp. And then vertical tangents. Notice I didn't say horizontal tangents, just vertical tangents. If a function it's like you can tell a function is going to be a function by visually looking at the VLT, the vertical line test. You can tell a function is going to be differentiable if it doesn't have any corners, it doesn't have any cusps, and it doesn't have a vertical tangent. A vertical tangent looks like this. It's coming along nicely, and then for a moment it shoots up vertical, and then it heads sideways again. And there is a moment right there where it's at its steepest point and it achieves a slope of infinity. That's a vertical tangent if any of the slopes happen to be infinity at any particular point. So you've got corners, cusps, and vertical tangents. That's your visual cues to look for differentiability. Oh, and no discontinuities. So you're also looking for no gaps, no holes, no asymptotic discontinuities, no oscillating discontinuities. So that's visual differentiability. Now we've got to do the algebraic differentiability proof. All right, so the next one is proving differentiability algebraically with limits. And you've been doing this without even knowing it. So you're ahead of the game already. Okay, you algebraically using limits. How many limits does it take to prove continuity? How many limits does it take? It takes 2 limits and then plus the point. How many limits does it take to prove differentiability? It's going to take 4. Okay, so because it takes the same 2 for continuity and then 2 more, and you've been doing this, we're just going to formally define it now. So you first have to prove, step 1, the limit approaching a from the left of the original function and the limit approaching a from the right of the original function is all equal to the point value at f of a itself. That is what we did all of chapter 2. Once you've proven those 2 limits and the point, then you move on, and then you have to prove the limit approaching a from the left of the derivative, f prime, is equal to the limit approaching a from the right of the derivative, f prime. This is the same as proving continuity in a tangent. And we did it with, find the values of p and q that make that true. Same thing. So you've been doing this already. We're just formally now defining it as this is what is required for differentiability. And if you follow that format, then you should have no problem with every single question. All right, so here's what it's going to look like. Example A. Is f of x equals x squared differentiable at x equals 0? Visually, you should already know the answer. What does x squared look like? A parabola. Okay, first question, is the parabola continuous? Of course, a parabola is continuous. There are no holes, there's no gaps, there's no asymptotes. Okay, does a parabola have any corners or cusps or vertical tangents? No, again. So we already know that the answer to this is going to be yes. Now we need to prove it. And so what we need to do is we need to prove, in our proof, 5 things. We need to prove that the limit approaching 0 from the left of f of x. We will need to prove the limit approaching 0 from the right of f of x. We will need to prove f of 0 itself. And we will also need to prove the limit approaching 0 from the left of f prime and the limit approaching 0 from the right of f prime. So the format is always the same, 5 things. And you're just going to go through and prove each one of them. The first 3 need to be equal and the second 2 need to be equal, and then you've proven it. All right, so let's drop 0, negative into the parabola. What do I get with 0, negative in there? Okay, 0, negative squared, 0 plus. All right, when I plug in 0, positive, and I square it, I also get 0 plus. And when I drop in 0 into the parabola, it is 0. So we have now proven the first 3. We've proven continuity. The second 2. Have you done x squared enough that you know the derivative of x squared now? 2x. All right, so we are going to use the limit of 0 minus in the function 2x, and the limit of 0 plus in the function 2x. So if I plug in 0 minus into 2x, what do I get? What's 2 times 0 minus? Still 0 minus. And when I plug in 2 times 0 plus, that is still 0 plus. Are those approaching each other? Okay, we don't have to, don't matter, it doesn't matter that one is 0 minus and one is 0 plus, because we know the parabola is coming down this way and then it's coming down this way. So yes, we have a minus slope coming down this way and we have a positive slope on this side, but what are they approaching? Okay, they're approaching the vertex and they're both approaching 0, and so that is fine. And so it is now, we have proven differentiability also. So we knew the answer was going to be yes. We have now proven it because the first 3 matched for continuity and the second 3 matched for differentiability. Okay, let's try another function that we already know the answer to, but we're going to practice proving it. Yeah?
They don't all need to be equal, right?
No. Just the first 3 have to be equal to each other, and the bottom 2 have to be equal to each other. It just so happened they were all 0 in this case. All right, is f of x equals the absolute value of x minus 2. Is that differentiable at x equals 0? Visually, we already know the answer to this. Visually, does the absolute value of x minus 2 have any gaps or holes or asymptotes? Okay, gaps, holes, or asymptotes in the absolute value of x minus 2? No, so we can say with confidence that it is continuous. But visually, does it have any corners, cusps, or vertical tangents? Yes, and so we can say although it's continuous, it is not going to be differentiable. Now, can you prove it? All right, so our proof is going to be very much the same. 5 things. The limit approaching 0 from the left of the original function, the limit approaching 0 from the right of the original function, and f of 0 itself, compared to the limit approaching 0 from the left of the derivative value and the limit approaching 0 from the right of the derivative value. All right, so the original function, if I drop 0 minus into this and then I subtract 2, I'm going to get 2 minus. If I plug 0 plus into this and subtract 2, negative, I'm going to get negative 2 plus. And if I drop 0 into it, I'm going to get negative 2. So none of that is a surprise. Oh, negative 2. Sorry, thanks. A little bit higher. And so we have continuity. You still get a negative 2. It's just a little higher than negative 2. All right, how about f prime? What do we know? Do you know enough about the absolute value graph? Is it curved? Are the sides of the absolute value graph curved? They're just 2 lines. You don't need calculus to know what the derivative is. When you're on 0 minus, you're on this side of the absolute value. And what slope does anything on this side of the absolute value have? That's negative 1 slope. When you're on 0 plus, you're on this side of the absolute value. And that one always has slope of what? Positive 1. Now we have our first problem, where negative 1 and positive 1 are clearly not the same as each other. And so this is not differentiable. So it was, yes, it was continuous, but it was not even differentiable at all. Okay, our last one. Is the following function, f of x equals, okay, now we're going to have a piecewise function, x cubed when x is less than or equal to 0, and 3x, oh, wrote it wrong, copy it right, 2x when x is greater than 0. Is that differentiable? at x equals 0. You're just going to take yourself through the exact same thing. Okay, this is a piecewise function. Now, you don't have to totally be able to picture it. It's going to be a cubic attached to a line. But you don't have to be able to draw a perfect graph to be able to prove whether it is or isn't differentiable. You just need to take yourself through those steps. So we're going to look at our 5 criteria. The proof of the limit to the left and right, as well as the point itself. And we're going to look at the proof of the limit of the derivative to the left and the right. F prime, oops. All right, so the left-hand value of the limit, if I look at that piecewise function and I check 0 minus, I'm going to get 0 minus to the third, which is still 0 minus. When I check 0 plus, I'm going to get 2 times 0 plus, which is 0 plus. And when I check, so we can clearly tell it is continuous. What if it's not? I haven't done any of those samples with you, but what if it would not end up to be, go back. Yeah, stop. If you can't even get past continuity, it's clearly not going to be differentiable because you have to be continuous to even move on to the differentiability part. All right, how about x cubed? Have you done that enough times to know what its derivative is going to be? 3x squared. Okay, and so we will be having the limit. And if you haven't, then you'll have to do it either Leibniz or Newton's way, but this will be 3x squared. You are welcome to look back at old homework and, copy the derivatives you've done earlier. You don't have to do all, if you've done the work once, then just take the answer of what that derivative was. And so when I drop 0 in there, I'm going to get 3 times 0 minus squared, which is going to be 0 plus. And then the bottom function is not a line or not a curve at all, it's just a line, and so its value is going to be 2. And so now you can see it is not differentiable because the values, the left and right hand derivative values, did not come out to be equal. So we say it is not differentiable. Sometimes when they ask you questions about differentiability, they'll say, where is it differentiable? Sometimes it's easier to answer the opposite question. Well, where is it not differentiable? Decide where it's not differentiable, and then it's going to be differentiable everywhere else. So if it's not differentiable at 2, then it is differentiable at all real numbers except 2. If it's not going to be differentiable at 0 and 4, then it is differentiable everywhere else.